In this series of videos, we will see how we can code a convolutional neural network. Now, this is something we have already discussed, which is the life cycle of any Keras model or any neural network which is built in Keras. And we have gone through each of these 5 steps in detail in week 1. But just a recap, it has 5 different stages of building a neural network model in Keras. It starts with defining the network, compiling the network, fitting the model, evaluating the model, and of course finally making prediction. And in all our coding example, we have used all the 5 life cycle of a neural network to achieve our goal. In this example, I have written a simple code for a neural network or a multi-layer neural network. Again, as you can see, I have only defined the network in this particular example. I haven't performed compiling the model, fitting or evaluating or making the prediction. At the time being, I just wanted to show you how different a model architecture looks when you are implementing it in a convolutional neural network and when you are implementing it in a multi-layer neural network. So I have just done this particular phase in the life cycle, which is defining the network. I haven't fed training data into my network, and so the remaining 5 steps are not performed. So as you can see, the first step is to import all the necessary libraries, and then what I have done is I have defined the input shape of my data set which I will be using for training. So here, as you can see, this 10 represents my input features, that is, it represents my column or the attributes in the data set. As you can see, the number of rows in your training data set is not a part of your input space of the network. So I haven't defined what my number of rows are while defining my input shape. I only mentioned 10, which is the feature space or the number of columns present in your data set. So this is done because during the training process, when we feed our network with the data set, it automatically takes in the batch size which we have assigned or which we will assign during our training phase. So whatever we have provided as a batch size, for example 32, so in that case it automatically takes the number of records for the first iteration for the first epochs to be 32, and of course the columns to be 10. So we don't have to exclusively mention that while we are defining our input shape. So in a multi-layer perceptron, the shape must explicitly leave room for the shape of the batch size used when training the model. That is why you could see I have kept a dimension to be hanging, right? I have just defined 10 comma because whatever be my batch size that I will be using for training, it would automatically be used in the shape, right? So here, as we can see, I have defined an architecture for multi-layer perceptron or a multiple layer neural network for a binary classifier, right? So here the model has of course 10 inputs, that is 10 features, and then there are three hidden layers with 10, 20 and 10 neurons respectively, and one node in the output layer. And I have used ReLU as an activation function for all the three hidden layer, and the sigmoid activation function, since it is a binary classifier, I have used that in my output layer. So one more thing you could notice here is that I am using a functional API, right, of building a model and not a sequence model. So that is why literally this value is assigned to a variable visible, and that is then used here and so on, right? So let us go ahead and run this code. As you can see, since I have asked to print the model summary, I am actually able to visualize what are my input in each of the layer, its output shape, the number of parameter that needs to be trained in each of my layers of my neural network, and finally these parameters get added up to find the total parameter that needs to be trained. Now you might already know how we got this 110. The reason why I got this 110 is that because my input shape is 10, that means I have 10 nodes, 10 input node. I will also have one bias, so that makes 11 nodes in the input layer, right? And that is connected to a hidden layer with another 10 nodes. That means 11 into 10, which is 110, right? So that is how I get this 110, and similarly we can find the number of parameters for each of the layers. So this, and of course since I have I have asked my model to plot the graph, I could actually see the graph here called as multi-layer perceptron, which actually gives me, again, not a very detailed picture, but at least a few idea of how my model looks like. So clearly it says that it has an input layer and we have three hidden layers. So dense underscore 1, dense underscore 2 represents our three hidden layer, and of course the last dense underscore 3 represents our output layer. So this is the next set of code we will discuss, and here I have written a code to define a CNN architecture, a convolutional neural network architecture for a image classification problem. As like the previous example, again I am just defining the network. I am not actually feeding any training data set, and therefore the step 2, 3, 4, 5 will not be present in the code. So as you can see, because I am performing a convolutional operation, I'm performing a CNN, I'm building a CNN architecture, I have few more classes to be imported from my Keras library. And here, as I have mentioned, I will be building a CNN model or a CNN architecture for an image classification. Now, one major difference that you could see here is the input shape. So I have given shape is equal to 64, 64, 1. So that means I am saying regardless of how many images I will have in my data set, each of these image will be of shape 64 cross 64 cross 1. So cross 1 means it represents channel. So channel is equal to 1 basically means that in my training data set I will be using black and white images or grayscale images. So in short, this model receives a black and white image of size 64 cross 64, and that is fed into a sequence of two convolution and pooling operations for feature extraction, followed by a fully connected layer and an output layer to actually perform the classification operation. So as we know, our CNN has two parts to it, the feature extraction, which is performed by the combination of convolution and pooling operation, and then we have the actual classification part, wherein which we have fully connected neural network, right? So let us go ahead and run this code and investigate its summary. So again, since I have asked to print the model summary, I have something like this. And if I go and check the place where I have my code, I will also have a small description of how my model architecture looks like. So as you can see in my first convolution layer, that is here, I have 32. So 32 technically means I have 32 kernels of size 4 cross 4. Right? So if I look here, I have this 32 represents I have 32 filters or 32 kernel, each of size 4 cross 4. So technically that means I have an image which is 64 cross 64, and my first convolution operation has number of filters to be 32, the size of the filter to be equal to 4 cross 4, and there is padding is equal to 0. I have stride is equal to 1. Now in this convolution layer, I haven't given my stride, but if you haven't provided it, of course it goes with the default value, how the convolution con2d function is defined in the Keras library, and by default stride is equal to 1. So going back to the equation, n plus so this is our equation, n plus 2p minus f by s plus 1. So n is nothing but the size of the image, which in our case is 64, plus 2 into padding, so there is no padding, so 0, minus f, which is the size of our filter or the kernel, which is 4, divided by the default stride, which is equal to s, which is s, that is equal to 1, and that plus 1. And doing this, which will give us 60 plus 1, which is equal to 61, which means the resultant of a convolution operation on my 64 cross 64 image is now a 61 cross 61, and of course the number of channels comes from the number of filter, which is 32. So I have cross 32. So this is exactly what is represented here, 61, 61, 32. And similarly, number of parameters. So we know that I have the filter of size 4 cross 4. So I have a filter of size 4 cross 4. So that means 4 into 4. So I have these many number of numbers or parameter for one filter, which is 16. And then I have 32 such filters, right? So 16 into 32, which is equal to 512, right? And then 512 plus my bias, that is I will have 32 bias, so 512 plus 32, and that is 544. So that is why I have this 544 here. So this is my first convolution operation. And of course, after the convolution, it would be after we have performed the convolution operation added with the bias, that is 32 bias values, we will pass it through our activation function ReLU, right? So that is, at that point we end up with an image which is 61 cross 61 cross 32, which then passes to the next operation, which is the pooling operation. So this is the Keras page for maximum pool 2D layer function. And here, as you can see, it says that about strides. So if I haven't specified what my stride is, so stride specify how far the pooling window moves for each pooling step. So if in my program I haven't mentioned what is the stride, it takes the value, default value none, and the default value none points to the pool size. So whatever you have given your pool size, which is our window size in our pooling operation, that automatically becomes our stride value. So as you can see, soon after my first convolution operation, I have my first pooling operation, and the pooling operation I am doing is a max pooling, right? So I have my 61 cross 61 cross 32 image, which I have got after performing the first convolution operation. So according to my code, it says that the pool size is 2. So that technically means in the equation we will be using, that resonates with the filter size, which is now 2. And here, as you can see, I haven't used stride, right? So I haven't specified by how much point my window has to move. So since I haven't specified that, as I have mentioned, it will take the default value none, and the none value points to what your pool size is. So what happens is that my stride, since I haven't specified it, it becomes same as my pool size, which is 2. And then I am doing my same equation, n plus 2p minus f divided by s plus 1, and that is equal to n value is 61 plus 2 into padding, that is we have no padding, so 0, minus f. So usually we don't do any padding operation on our pooling operation. So padding value is 0 in this equation, minus F, which is 2, divided by stride, which is 2, plus 1. So that will give us, when you perform this operation, 30.5. And as I have mentioned, if you have a decimal point, we round it to the lowest number. So that is how we get our value 30. Now that is the same value which you could see here, right? So that is how I get 30 cross 30, and of course the my depth of the image, which is 32. So this result in a much smaller image of size 30 cross 30 cross the depth 32, right? And as you can see, the number of parameters is 0, right? Because I'm performing a pooling operation, so there is no parameters to be learned. All the values, my size of my window, my number of strides, all those are hyperparameters. So technically there is no parameter that has to be learned for my pooling operation. So that is why it is represented as 0. So similarly, I have my next two convolution plus pooling operation that is being done before it is being fed into a fully connected neural network. So after pool 2, whatever is the size of my image, so after my pooling operation, the size is, after my second pooling, size is 13, 13, 16. So at that point, what I do is I flatten that particular image and then feed it into my fully connected neural network, which has now got 10 neurons, right? And 10 neurons, and I'm performing an activation of ReLU, after which it is connected to my output layer. And since it is a binary classification, I just have one node in my output layer, and I am using a sigmoid activation function. Here also, as you can see, I haven't used the sequential API approach, but I have used functional models, right? That is why technically, again, starting from this position itself, I have assigned my input shape value to a variable visible, passing that variable visible to my first convolution layer, and so on. So this is an example again of a functional API. In this code, I have rewritten the architecture of our previous convolutional neural network. And as you can see, now I have a sequential model creation, which is very advantageous, right? So you could see how you could see as like my previous CNN example. Again, I have my first convolution operation has 32 different filters, each of filter size 4 cross 4. I have used an activation function ReLU, and the input shape is 64, 64, 1. So it is basically the same convolution operation as from my previous example. And then I have done a max pooling. Similarly, my second convolution operation plus max pooling. Now here what you could see is that after my max pooling, I have flattened my image, and after that it is passed into my fully connected neural network. So if you go to the previous example I have shown you, in this example I haven't flattened my image before it was fed into my fully connected neural network. So let us run this program, and as you can see, now the total number of parameters is different. It is 35813. Whereas if I run the previous code, see, I have only 8933 parameters. So basically, because I haven't flattened my image before it was fed into a fully connected network, what happens is that here I have only 170 parameters that has to be learned. But we know that if it was flattened, then it means I have to learn the number of parameters. So here I will, if I flatten after this layer, after my max pooling operation, then what happens is that I have 13 cross 13 cross 16. So I have flattened my image, right? And then of course I will add a bias into it, so +1, so that is 2705, and that is connected with a fully connected layer of 10 neurons. So that 2705 into 10. So 27050, that should be our value, but we didn't get that 2705 at this value. We just got it as 170. Whereas if I go back to my new example and if I rerun the code, here you could see that my parameter calculation is coming as correct, 27050. So don't forget to flatten your object before it is being passed into a fully connected layer. Otherwise, as I have shown in this example, you will have the total number of parameter calculation to be wrong.